speaker is Anatoly Klypin. He's going to talk about making more catalogs for large scale projects.
Okay, now we're going to change scales by a few orders of magnitude, and I was trying to estimate how many. My guess is something like 15 orders of magnitude in mass. It's interesting physics, lots of interesting kind of results, and coming in planning this, my collaborators on that project. So now we're talking about significant observational effort to map the universe in different properties of galaxies. That will be large-scale observations. Now we already have that Bose observations, which we already have been studying. More coming will be Euclid. There also will be Rosita, and just you name it, all is there. What's at stake? It's lots of interesting kind of physics, improving cosmological parameters. This is one. It's coming. The also evolution of galaxies with the redshift, the clustering of galaxies, velocity dispersions, potentially evolution of omega lambda with redshift. So it's all kind of at stake here. Theoretical requirements to kind of face that kind of observational data is very significant, very difficult. It just way too many. Okay, if you think about it, this is the map which is here. How many galaxies we are going to observe? That's millions upon millions. So current sample, which is a Bose, which is here, it's 1 gigaparsec kind of scale-ish, which will be this one. The Bose will be extending, which will be here. We have a Lyman alpha and quasi absorption line. So it's all these kind of very large scales, and that's should be modeled very quickly because they require lots of realizations, not just one, but about 10,000. Okay, and each one should produce a clustering of galaxies from fraction of megaparsec up to hundreds of megaparsec with a very high accuracy, because it's an accuracy which is will define your cosmological parameters and evolution and everything else. So it's very kind of a difficult kind of project. We'll come to that. At the heart of the whole thing is the relation between dark matter and baryons, because at the end of the day, we will have only dark matter with that resolution, with that kind of accuracy. We cannot possibly do any hydrodynamics. Just forget about it. We're talking about something like 1 billion galaxies. So now we cannot possibly simulate it at this moment, that kind of amount, but we kind of looking at that. So now it's a relation between, this is what we kind of already know from Severina, Dutton Macho, and whatever it is. It's a relation between virial mass and the stellar mass. It's actually reasonably tight. If you go to small objects, the scatter is big. If you go to larger objects, look at this one, that will be, which will be here. The correlation is relatively tight, and so we're using that through Hell abundance matching for different kind of techniques, how to estimate the clustering of galaxies and their motion and produce more catalogs. This is an example. This is in this case, the simulations were used. It was a multi-duct simulation, which is 66 billion particles or something like that, 2.5 gigaparsec box with the Hell abundance matching, which is here. In order to do Hell abundance matching, we need to measure accurately stellar mass function, which is here, the different samples here. And afterwards, you match abundance of galaxies, a function of redshift. This all should be matched. Once we have it, and that doesn't have any free parameters, at the end of the day, we produce clustering properties, different parameters of observations, how we kind of scoring that. And this is an example from Sergio Rodriguez Torres, 2015. That will be correlation function and redshift space. That's a monopole, that's a quadrupole. That will be simulations will be blue, and observations will be in data points. And it matches reasonably well. If you look at the outside, so the inner part is not that bad. So if you look at the outside, you see some kind of deviations. Deviations are very interesting, and that actually is a problem with observations. If you have any problem with observations, you blame observations. But I know that it's true. And you can ask me later on, why is that? So now that's kind of an example. But the problem with that, there's only one realization, and we need to have 10,000 of them. Okay? And that's definitely very difficult to do it numerically. So we need to do it, but much, much faster. That's a clustering of galaxies in the bus, which is again data points, which will be here with the error bus, and this will be clustering in that simulation. So we're doing pretty good in that respect, but now we need to do it much faster, much bigger, and for different cosmologies and different redshifts and everything else. And this is a normal kind of a path here. It's run fast, cheap, large PM simulations, and afterwards do something good with those. So now I will address only two issues. One is the size of simulation box, which is a technical issue, but actually there's an interesting physics behind that. It's quite interesting behind it because it's a coupling of different modes on the longer waves, on the shorter waves. That's the way it's coming to, and this is also kind of thing here. And that's a requirement for the whole test. We need to know what simulation box to take in order not to drop some kind of physical effects. And also another issue will be distribution function of a density and the number of galaxies in a given cell. So large simulations are very useful. For us, those large simulations will be like observations. So we test all our kind of very fast simulations, again, high resolution simulations, you see how we match it, and afterwards we start to apply to observations and see what will happen. There is a different kind of method which people developed in that respect. QPM, Cole, Apache, and in our simulations, they're all of the same kind, but some of them more efficient than others. And of course, as you understand, our simulations are always better than theirs, which is at CPU time. But now let's have a look. The first is different box sizes, half gigaparsec, 4 gigaparsec, and we have large statistics of those. So altogether, around 15,000 realizations to tackle all the different effects. Cosmic variance is not now important. It's gone because you have so many realizations. The error bars, statistical error bars, are not visible when I plot a curve. It actually, it's the width of the curve, which is the statistical error bar. So statistics is not important. The resolution comes in the different kind of ways, and let's see what kind of simulation box we need to choose. The bigger the box, the better, because it's you cover bigger volume. At the same time, your resolution, your physical resolution, the force resolution goes down, and the mass resolution starts to become quite significant. So how we do that? Oh, by the way, and this one is quite important. So one of big those simulations like multi-DAC is about 1 million CPU hours, plus lots of data to analyze. One simulation, which I will be talking about, is 100 CPU hours. And it's very nice to see how results pop up like in front of your eyes, done. Like sit for half an hour, you get a lunch, one universe. You have another lunch, another universe, and keep going like that. So now the first thing is the testing. Okay, and there's a different ways of doing those tests. That's a comparison with the big multi-DAC simulations, which I select. So this is the mass function. So the curve and a plus minus 5% errors, that's a big multi-DAC mass function from 10 to the 15 up to whatever it stands at 12. And our simulations, which we call, I don't know why that's called glamour, I don't know what. Reproducing mass function within 5% up to a few times of a 10 to 12. And we're looking for like a, for both sample, we're going to 10 to the 13 and up. So we pretty damn good with very high accuracy, with a price which is very, very, very small. It's very reasonably good. This is a power spectrum. This is a 1% error. So within 0.5% error, we reproduce big multi-DAC. The wiggles here, it's actually cosmic variance in big multi-DAC because it's only one realization, 2.5 gigaparsec. So this is actually is a statistical errors in big multi-DAC. And this is first our effort on mock galaxies and their correlation function. So big multi-DAC was that full curve here, and GLAM simulations were blue points here. That's a cosmic variance in the big multi-DAC. Otherwise, we reproduce correlation function of mock galaxies from 100 plus megaparsec up to about 1 megaparsec, and there's a big progress because now we on this side we could go to actually interior part of and even see one heliton, which was difficult before. So now, how large should be simulation box? So now, if you look at this one, this is what kind of upcoming and existing samples. what simulation box we need to reproduce that kind of clustering pattern here. And you would like to be tempted just to put it in the whole box, right? And if you do that, you definitely is an observer. It's easy to do it. You don't need to think about it. As a physicist, you start to think about something else. You start to think about nonlinear coupling of different modes. No matter how big, how small is the box, some waves will be missing. You take this wave, will be wave which is bigger than that one. What's the effect? How those waves will be affecting your results? That will be affecting your box size. The papers written on that, analytical papers, how big and what effect it will be, and we'll see in the simulations how that will work. So this is a power spectrum of a dark matter, and you see the wiggles here. That's the baryonic oscillations. This will be our simulations will be here, multi-dark will be here. So we're doing pretty good in the sense of power spectrum all the way up to here. Fundamental mode, which is defined by the box size, in this case 1 gigaparsec, will be here. Everything above that cannot be reproduced because we don't have a big box enough. But at the same time, we're not really interested in that. But so this is zoom in on that part. This is where your peaks correspond to about 100 megaparsec scale. That cutoff in the box size is well outside. So we're actually doing very good job on everything which is relevant for clustering. Properties of galaxies, clusters of galaxies will be way below here. Cosmological parameters which is here, so we're not affected by any ways by longer waves. We could actually check that accurately whether it's true or not. So in this case, it's a ratio of power spectrum divided by fiducial power spectrum, which will be here. I will explain that, but it's done. This is a wave number here. Baryonic oscillations will be around here. Again, this is a 2%, this is 1% error, this is wave with 10. So if you go to from small box to bigger box, resolution declines. That's all these effects of resolution, which is naively kind of what you expect. In increased resolution, you get bigger K. But this domain is different. This is domain of emitting super scale, super sample models. There is a small effect if you have a look inside, but that small effect is like the 0.5%. So you reproduce a clustering on all the scales without any defects or any significant defects on small scales. Now, if you have a plot that for different blocks, because it's going all the way up to 1 gigaparsec, which will be here. If you plot the same at the 0.5 gigaparsec, you see clearly it will be defect. And that's well understood in analytics. We see that, but at the same time, if you go to 1.5 gigaparsec to 1 gigaparsec, on all possible scales, effects are minute. This is one of a test. Another test is a covariance matrix, which is definition which is here. You cross correlate value of power spectrum at different Ks, and subtract the K at K average, and you start to see some effects, something like that. Let's have a look at this one. That's covariance matrix. There's a diagonal component, which is a trivial, which is simply how many harmonics in a bin you have. That's nothing particularly interesting about it. If you go in that direction, the effect is increasing. So now that's the effect of nonlinear evolution. And you could do in different ways, plotting and dividing, and so on. This is covariance matrix. Covariance matrix provides another very, very sensitive test. We know how it should scale if there's no nonlinear effects. If nonlinear effects due to longer waves are missing, it should simply scale with the volume, inversely proportional to the volume. It actually does it. That's covariance matrix. Let me skip that, how it evolves. Redshift. This is covariance matrix at different Ks. Slice at different K prime, and that will be dependent on another wave number here. So if you take this one, so you see clearly effect of the volume. So the smaller is the volume, bigger, the bigger is the covariance matrix. The volume is increasing, covariance matrix goes down. Again, this is a trivial effect. Number of pairs with given separation will be bigger if the volume size is bigger. So you take 1 gigaparsec, we have so many independent pairs at 100 megaparsec. If you take 10 gigaparsec box, will be many more of those, and such covariance matrix will go down. But now if you scale it, and actually you see no effect. So it's a trivial scaling of a covariance matrix with a box size. That wouldn't be true if waves longer than the box size will couple with anything which is inside the box. Then you will see the scaling will actually be wrong. It actually is very, very nice kind of scaling here. So all statistical properties could be reproduced if the box simulation big enough, about 1 gigaparsec. You don't actually need to go to very large scales to reproduce all observable quantities here. So now if you look at that situation, this is about box size which you need to reproduce all the clustering properties of objects. Now this was one test. Another interesting issue which is not related with what we discussed before, but it's a separate topic. I have 5 minutes left. Okay, good. It's a distribution function. So now we get used to power spectrum, correlation function, clustering properties. There's another historical kind of statistics. It's a simply distribution of number of counts in a cell. So you can do it you can do it for dark matter. You can do it for galaxies. It's a very old statistics. Statistics is actually very interesting. But very difficult actually to get once you go to observations. We'll have some look at them. Now we also need to understand how the statistics happen with dark matter, because we will map dark matter into galaxies. We need to know what we're dealing with. So now that statistics, so we take a box size or cell size of given size. It could be sphere, could be box, doesn't really matter, and count what's the distribution function of those values. So if we start at initial redshift, at high redshift, it's all linear fluctuation, it's all Gaussian. The distribution is simply Gaussian. But it's known that it became very non-Gaussian very, very, very quickly. Okay. So now history of that, it goes back to Edwin Hubble. 1934, he actually published a paper, 44,000 galaxies in the sky. He did a counts on cell, and the statement was it doesn't look like Gaussian at all. It actually looks like a log normal. Okay, so Nair-Peebles 78 leak counts 10 by 10 arc minutes also finds the very broad distribution, which is not really Poissonian. Peebles 98 analytics cell counts is the integral over the power spectrum. Coulson-Lacey 91 argued from analytical kind of arguments that distribution should be log normal. The arguments, as we understand, are not really rigorous and not really correct. Different people found, and we kind of reconfirmed that, but very few actually find that actually is quite a bit different. We'll have a look. The field is pretty kind of alive and kicking. These are different quotes of from different papers. Recovering nonlinear density field, the galaxy distribution using Poisson log normal filter here, log normal filter there. Log normal distribution has a one free parameter. It arises when you have a random number we have which is a product of many independent Gaussian numbers. So now, in this case, each Gaussian number, but because it's a product, distribution should be log normal. And this is that log normal distribution has a one parameter sigma, the width, and it defines the whole properties. It's very nice property, very nice kind of a function. You can easily plot it, you can easily choose it and play with it. Now, there's nothing really magic about log normal distribution. In our astronomy, that should not be log normal. So in sense of pure statistics, it cannot possibly be. Okay, and it's very simple. If you take a box size of this side and say how many galaxies or what dark matter will be there, that will be the sum of values of each individual cell. If distribution function in that individual cell is log normal, sum of those will not be log normal. So in sense of statistics, mathematics, it cannot be log normal, but it can, maybe it's not terribly log normal. Let's have a look. Observations. That's from 2DF 2005, 200,000 galaxies. This is the distribution function for early types, for late types, and this is for cell 15 megaparsec. If you go to small size, it will be really wacky. It's very difficult to see anything. So now it looks okay, but not really good. So now this is a recent result, 2017. That's from SDSS, cell counts, 100,000 galaxies, 8 megaparsec cell. This is the counts, the blue, and this will be log normal. It's not terribly off, but not terribly good. You go to bigger cells, it starts to get more log normish, but still deviations are very significant. In that field, that kind of distribution, that kind of offset is not a good approximation. So now I made the same kind of analysis, but from galaxies, quote unquote, from big multi-duck. So in this case, I take all galaxies and subhalos with more than 200 kilometers per second. There will be 20 million of those, and that will be the distribution function. Number of galaxies, 1, 2, 3, 4, 5, smooth with some filter, that will be, and that's log normal. And that log normal distribution is actually not that bad if you look at that, but at the same time, it's not terribly good. Looking at this one, when I plot a function which is steeply declining, in a linear scale, you can hide lots of details. Plot function always an logarithmic scale if you don't see anything. So now, this is distribution function of more galaxies, and this is a log normal. You clearly see that it cannot possibly be. Okay, those effects with factor of 2, you can actually saw that and if you carefully look at the diagram. So it's not terribly good in galaxies. How it goes in dark matter, here's a plot. And it's actually quite remarkable plot because now statistical errors are basically none. So now this is at redshift 0, the different simulations stacked together, averaged, and everything in processes, different size of the box from 100 kiloparsec to 10 megaparsec, that will be 10 megaparsec, it will be 100 kiloparsec, this distribution function. It's also the same kind of behavior will be with the redshift. At a high redshift will be very peaky, and afterwards, as fluctuations will increase, you go to that direction. It changes by 12 orders of magnitude, which is a remarkable function, and now at the end of the day, we were able to approximate that function, which changed by 12 orders of magnitude at different redshifts, with the accuracy of a few %. But now what you see, there's no log normal distribution here. It actually asymptotically goes to R-2, the probability. At a small, at a big cell size, about 10 megaparsec, which is the way observations were before, it does look log normish, but actually if you start to fit, it actually is not terribly good fit. So now this is evolution with the redshift. You take, say, 1 megaparsec scale will be like that. At redshift 4.5, it's kind of skewed a bit, but not a Gaussian, not log normal. It keep going like that. It start to extend, and go to, because of plot multiplied by the density, will be flat. And this is our fits. You multiply by R minus by density squared. It's actually very nice function, for which we actually have a approximation analytics. Altogether, we produce all these different effects, and I have 2 seconds left. So now we compare different models, log normal, spherical informal model, there's some analytics, it actually started to get really good. And this double exponential fit, which we get from simulations. And this will be the error bars. So the error bars are quite small if you go to different scales for double exponential above with large sigma, small box size. Spherical informal model produce very accurate results with a few %. In the log normal, yeah, it's there, but it's not terribly good. So let's go to the summary. Log normal distributions for cell counts is a good toy model. Doesn't fail, but never excels. And a good toy model, it's very good for toys. There is much more accurate model, spherical informal model for large cells, and double exponential for small scale. So now we actually could nail it down with very, very, very high accuracy. Simulations on for mock samples, simulations with box size from 1 to 1.5 gigaparsec actually sufficient to reproduce all possible or foreseeable statistical properties of galaxies in the universe. And this is what's going to do it. And it's very, very fast. We could produce different simulations in a large number.
So, thank you very much.
Phew.
Time for one short question. So, maybe I missed that. What was the difference between optical and GLAM? The algorithm different?
Yes, it's algorithm. So GLAM is a PM simulation with a large mesh. And multi-duck is actually multi-duck was a gadget simulation. Yeah.
I think we have to move on to the next speaker. So thank you. Our next speaker is Lognormal. He will talk about deep learning forecast.
Let me also mention that the group photo is up on the website, and you can click on it and you download the full resolution.